All right. So in the previous video, we talked about what to do if we are working with a linear, homogeneous differential equation that is both second order and has constant coefficients. And the idea there was to use the auxiliary equation, which is a quadratic equation in the second order case, solve that, and then based on which of the three cases that we talked about, we can use those solutions to produce a general solution for the original DE. So let's take a look at this one first. We want to solve this differential equation. Y double prime minus 12y prime plus 36y equals 0. Now the auxiliary equation for this is going to look like m squared minus 12m plus 36 equals 0. Okay? And remember, basically all that is our y double prime becomes m squared, our y prime becomes m, and our y becomes a 1. This ends up being our constant term here. I want to solve this, okay? And this factors to m minus 6 squared equals 0, giving me m equals 6. This is the case where we end up with one real repeated root. Repeated because m minus 6 is technically showing up twice in this factorization, m minus 6 times m minus 6. In that case, we saw how to construct a general solution. So remember, y1 would equal e to this solution times x, 6x. y2 would be equal to x e to the 6x. Remember, we used reduction of order to find that second solution. That means my general solution is c1 e to the 6x plus c2 x e to the 6x. Notice how fast that was. That's uncharacteristic of the problems in this class. They usually take a pretty long time. But the work that we've done here has reduced. We put in a lot of work into developing those techniques and those results, and now using them is actually very quick. Let's check another example. Let's try another example and see how this works. So 4y double prime minus 4y prime minus 3y equals 0. Another case of a second order linear homogeneous equation with constant coefficients. That's all of that needs to be true for me to use this stuff. It's also an IVP, so y of 0 equals 1, y prime of 0 equals 5. I'm looking for a specific solution here. Let's begin by finding our auxiliary equation. This will become 4m squared minus 4m minus 3 equals 0. Okay? Now, this is not an algebra class. I don't need to walk you through factoring and stuff like that. However, I have my own way of factoring quadratics with a leading coefficient not equal to 1 that I still like to show even more advanced classes like this, in case you haven't seen it before, because it's really cool. I like it. It starts off in what might be a familiar method that you've seen before. You do the leading coefficient times your constant, 4 times negative 3, which is negative 12. And then you take your linear coefficient, the negative 4 here, and put that down here. You're looking for two numbers that will add to negative 12 and multiply to negative 4. Very easy to see that negative 6 and 2 will do that. Most of you have probably seen a technique that at least starts this way. But this next step is where I think it diverges from what a lot of people have learned. We're going to take both of these numbers and divide them by the leading coefficient of this quadratic, which is 4. Simplifying as much as possible. 1/2 there, negative 3/2 there. This tells me how to factor the original quadratic. I read these fractions from the bottom up, 2 and negative 3. That's going to give me 2m, that's where the 2 is coming from, minus 3. And then here, 2m plus 1. It's plus because that 1 is positive. 2m plus 1 equals 0. That's guaranteed to work every time. It's a fantastic little factoring technique. If you've already known that and you're thinking this is old news, stop wasting time on that, fine. But a lot of people I have found never learned this full technique, and it just makes these problems go faster. Anyways, here's our two solutions. M equals 3/2, or m equals negative 1/2. Notice in this case, we're dealing with two distinct real solutions. So that means my fundamental set of solutions is going to be y1 equals e to the 3x over 2, or I could just call it 3/2 x if I want. y2 is going to equal e to the negative x over 2, or negative 1/2 x if you prefer. These two solutions we already know are going to form a linearly independent set, and so I have y equals c1 e to the 3x over 2 plus c2 e to the negative x over 2, and that there is my general solution. Okay, again, really all of the work goes into just factoring. Oh, sorry, I shouldn't have boxed that off. I forgot that we're dealing with an IVP. That's okay. We'll deal with that in a second. What I was going to say was essentially all the work just boils down to solving a quadratic equation, which is algebra. It's easy stuff at this point. Okay, but let's figure out what C1 and C2 have to equal in order to get a specific solution. Y of 0 equals 1. So let's start with that. Y of 0 equals 1 implies that 1 is equal to, plugging a 0 into each one of these is going to give me a 1 here and a 1 here, reducing this to C1 plus C2. What is y prime equal to? I have to take derivatives here, so I'm going to get 3/2 c1 e to the 3x over 2 plus, minus 1/2 c2 e to the negative x over 2. Okay, and then plugging a 0 in for that, I'm going to get y prime of 0, which is supposed to come out to, they said 5 up here, 5. Okay, is going to imply that 5 is equal to, again, plugging zeros into this is just going to give me 3/2 c1 minus 1/2 c2. Okay, let's simplify this. 1 equals c1 plus c2. Multiply everything by 2 to clear those denominators. 10 is equal to 3c1 minus c2. These are ready to be eliminated, so I can add 11 equals 4c1, which implies that c1 equals 11/4. Okay, let's plug this in up here. 1 is equal to 11/4 plus c2, which implies that c2 is equal to 1 minus 11/4. That would be negative 7/4. And so my solution after all of that is y equals c1, which is 11/4, e to the 3x over 2, minus 7/4, there's my c2, e to the negative x over 2. Okay? Usually I won't go through all of the work of solving an IVP this way, but it's good to see it every now and again. So there's my general, or my specific solution for that IVP. Let's look at another example. This time, we're going to solve 2y double prime plus 2y prime plus 1 equals 0. Okay, now if I try factoring this, if I keep working at it, I'm going to find that I'm having a hard time doing that. So I'm not going to solve this by factoring. I'm going to use the quadratic formula instead. According to the quadratic formula, well, actually, sorry, let me first find the auxiliary equation. It would be 2m squared plus 2m plus 1 equals 0. Now we'll apply the quadratic formula. M will be equal to negative b, so that's negative 2, plus or minus the square root of b squared, that's 4, minus 4ac. 4 times 2 times 1 would be 8. All over 2a, that would be 4. This is equal to negative 2 plus or minus. This becomes negative 4 in here, and the square root of negative 4 is 2i over 4. Or this could be written as negative 1/2 plus or minus 1/2 I. Okay, this is my my solution set. These two complex conjugates are my solutions to that differential, or that auxiliary equation up there. Now again, this is a case 3 scenario, and look at what we use in case 3. this will end up being our general solution. The a and the b that's showing up here, e to the ax and sine of bx, or cosine of bx, are coming from those that complex number, that a plus bi or a minus bi. So in my case here, a and b are equal to negative 1/2 and positive 1/2 respectively. Okay, so I can use I'm going to use those in my solution. My general solution is going to look like y equals c1 e to the ax, which is negative 1/2 x, or negative x over 2, times sine of bx, that's 1/2 times x, or again x over 2, plus c2 e to the negative x over 2 cosine of x over 2. Okay, now you might be looking at that and you might be thinking, well, hang on, I said that this is a positive 1/2, but it's plus or minus. How do we know if it's positive or negative 1/2? And the answer is that it doesn't matter which one you go with. Remember, whether you plug in a positive or a negative of that 1/2 in here, cosine is an even function. It absorbs that negative anyways. Sine is an odd function. That negative can be brought out, but it would be absorbed in that constant anyways. So we go with the positive just to make it look simpler, right? Also, I think in my solution that I wrote back there, I think it was cosine that came first and sine that came second. Obviously, that doesn't matter because it's the same thing. Whether you put cosine here and sine here, or sine here and cosine here, same thing, right? Finally, we do have a common factor of e to the negative x over 2 in both of these terms. You could factor that out if you want. There's no problem with that. I just didn't do that here. But that would be our solution. So again, the goal here, once we had our auxiliary equation, we got our complex conjugate solutions, and we just used the a and the b from that in that general solution that we derived back for case 3. All right, so we've kind of seen one example of each of those 3 cases. Let me zoom in a little bit. Now we want to see what to do if we move beyond the second order case. I'd like to look at higher order equations. What can we do there? So I'm going to, I think I'm running out of space on my device here. I'm going to just go through the derivation, or not the derivation, an explanation here, and then I'm going to create a third video just to do these last 2 examples. But basically what we did in the second order case generalizes really nicely to the nth order case. Remember, we came up with our approach in this section by looking at first order DEs. We saw that in the case of a first order homogeneous differential equation with constant coefficients, the solution would definitely look like, or a solution would definitely look like e to the mx for some constant m. And then we showed that making that assumption in the case of a second order equation of the same type was fruitful. It gave us the general solution that we wanted. That assumption will continue working for higher order equations. And all we really need to do is see what happens in those 3 cases in the event of a higher order DE. So let's suppose we're working with an nth order homogeneous linear DE with constant coefficients, an minus 1, dot, dot, dot. I don't know how many terms are in here because we don't know what n is, but a1, a0. This thing will have an auxiliary equation as well, and we find it the same way we did in the second order case. This nth derivative of y is going to become an m to the nth power. This n minus 1th derivative of y becomes m to the n minus 1, and so on and so forth, all the way down to this, which turns into a constant term. What we have now, instead of a quadratic equation, is we have an nth degree polynomial equation. And wrapped up in the solution to this is a lot of algebra, a lot of things that you learn in a pre-calculus class, intermediate algebra class, regarding solutions to polynomial equations. Okay? But so we're not, again, it's not an algebra class. We're going to be using some terms like multiplicity and stuff here that hopefully you remember what those mean. And if not, when we work through the examples, it should become a little more clear. But when we're looking for solutions to this thing, we still end up in 3 possible cases. We can find distinct solutions, so solutions that only appear from a single linear factor once you factor this. We can have repeated real roots, and in the case of an nth degree polynomial, that repeated root can repeat more than twice. It can repeat up to n times, and we call the number of times that root shows, the factor that gives us that root shows up in the factored form. We call that the multiplicity of that root. But in the event that we have a distinct real root, we'll be able to use the following solution: y equals e to the mix, where mi is that one distinct root. If we have a repeated root, kind of like what we did in case 2 of the second order case, we can use the solutions e to the mjx, and then a second x e to the mjx, and then x squared e to the mjx. In the case of a second order equation, we had these two guys to form our general solution. But if the multiplicity of that root is even higher, we can keep raising the power of that x there, make that an x squared, x cubed, so on and so forth, until we get to x to the k minus 1th power. Again, k is the multiplicity of that root. So all of those would be used in our fundamental solution set. In the case of complex conjugate roots, we have the same result that we had in the second order case. We still have, let me go back to that page. We still have e, here it is, way down here, e to the ax cosine of bx and e to the ax sine of bx. We'll use both of those in our fundamental solution set. So these can get messy depending on how big the, how high the order of this equation is, but mechanically it all kind of breaks down to the same sort of steps. So like I said, I'm going to make a third video. I'm going to stop this one here, but we have 2 examples of third order equations that we're going to look at applying these results.